So for reactions of aldehydes and ketones, the one thing which is very important we have to remember that is this functional group C double bond O. As you can see, C double bond O, or which is also known as carbonyl group, that is common in both aldehydes and ketones. For example, if I place both alkyl groups with this, it gives us ketone. And if this carbonyl group, one of the vacancy that is occupied by an alkyl group and another one with the hydrogen, that gives us aldehydes. So it means that the reactivity of these aldehydes and ketones that depends on this carbonyl functional group. But remember one thing, as I said earlier, that the names of these functional groups are different. For aldehydes, we consider this as a whole functional group. And the name of this functional group, that is formyl group, while this one is called carbonyl group. Clear? But similarity is in their reactions. This functional group is basically carbonyl group is responsible for their reactions. So for understanding, let's consider this carbonyl group, and I'm leaving these two vacancies vacant. It depends on us whether we want to make it an ketone or aldehyde. So this carbon and oxygen have electronegativity difference. So due to which oxygen is being more electronegative, gets partial negative charge, and this carbon is partial positive charge. So it means that this carbon of our carbonyl group that can behave as electrophilic center, right? Or we can say the nucleophile that can attack on this partial positive carbon atom. So when nucleophile reacts with these aldehydes or ketones, so this nucleophile will attack on this partial positive carbon atom. So for reactions, we can say that there will be nucleophilic addition reaction. Why we are calling it nucleophilic addition reaction? Suppose, let's, for the sake of understanding, take this carbonyl group, the partial positive, partial negative, and we have this reagent which can produce nucleophile, right? So on ionization, let's say this reagent produces nucleophile along with positively charged hydrogen ion. So this nucleophile that will attack on this partial positive carbon atom. And to accommodate this new dative bond, which is formed by the nucleophile by giving it a pair of electron, this pi electron goes to oxygen atom, which is being more electronegative, takes this pair of electron. So as a result, what we get this product O negative. So I can call it alk oxide ion or simply oxide ion. You can say it is an anion, right? Now, being negatively charged oxygen, it has an extra electron, so that can attack on partial positively charged hydrogen ion, and we get this product, which is OH. So we can say that nucleophile is added on the carbon, as you can see here, and hydrogen of the reagent that is added on the oxygen atom. So that gives us hydroxy compounds. For example, let's take a particular example. If I take HCN as an example, hydrogen cyanide. So CN will behave as a nucleophile. So, what product we will get? Let's see if we have an aldehyde or ketone, right? And we treat it with hydrogen cyanide. So, the Cn negative that will attack on this carbon, the pair of electron will shift on oxygen, and we get this O negative and C triple bond N, nitrile group. And now this oxygen, which is negatively charged, that can accept hydrogen ion. So this hydrogen ion can be accepted from the solvent, which is water, or can be accepted from the hydrogen, another HCN molecule. So that will give us a product which has OH group and C triple bond N, right? So here we have OH group on the second carbon, and we have seen that one of the carbon atom is also increased in our product. So these products are basically nitriles. And in these nitriles, let's say if this one is our first carbon, so 1 and 2, or you can say this carbon with which the functional group is attached, we can call it alpha carbon. So alpha hydroxynitriles. So we can say that we will get hydroxynitriles as a product whenever we treat aldehydes or ketones with this hydrogen cyanide or any reagent just like that, which can produce a nucleophile. Is it clear? And the type of reaction that is nucleophilic addition reaction. So let's see these type of reactions. But another type of reactions, as I said yesterday, one more thing, when we have aldehydes and we treat them with oxidizing agent, so we know that aldehydes are oxidized to carboxylic acids. And the reverse of oxidation, that is reduction. So it means that carboxylic acids, they can reduce to aldehydes. And now we also know that alcohols, when they are oxidized, they give us aldehydes. And when they are reduced, then aldehydes will give us alcohols. And remember one thing, that primary alcohols, they give us aldehydes, but if we take secondary, then their oxidation gives us ketones, and the reverse of that is reduction. It means the reduction of ketones gives us secondary alcohols. So now here, as we are discussing the reactions of aldehydes and ketones, so let's talk about the reduction. So for reduction, we have two main reducing agents. So reducing agent which we use for the reduction of these aldehydes and ketones, number one, that is lithium, aluminium, and H4. So the name is lithium tetrahydroaluminate. And the second one is NaBH4, sodium tetrahydroborate. So actually, these two are reducing agent. And remember one thing, this one is strong reducing agent
Sir,
as
can you say
compared, sorry,
can you say the name?
it's lithium tetrahydro. Okay, you can simply remember their name. If you ionize them, you will get lithium ion and you will get AlH4 minus 1. And we know that aluminium is a metal, so it means the oxidation number of aluminium here will be plus 3. So hydrogen is actually behaving as a hydride ion. Here it has minus 1 multiplied by 4. Remember, it's an exception for hydrogen. Normally, what we say that hydrogen in combined state shows plus 1 oxidation state. So that's why for hydrogen we are using word hydride. Is it clear? So 4 hydride ion means tetrahydride. So for the naming, we use tetrahydrido as we use for chloro, bromo, ido. So similarly, hydrido. Is it clear? So lithium tetrahydrido aluminate. And same is here. Actually, these are the reducing agent. They are the main source of hydride ion, H negative ion, which is used for the reduction of aldehydes and ketones. And when we talk, compare these two for exam point of view, remember lithium aluminum hydride is strong reducing agent. So that's why the conditions for this lithium aluminum hydride, or you can say tetrahydroaluminate, that is in presence of ether means dry condition, no water. But this one we can use aqueous conditions. Why? Water shouldn't be there because it is a strong reducing agent, so it can even react with water. So we use ether. So you can see here, look at that. We can use them for the reduction. We have lithium tetrahydroaluminate or sodium tetrahydroborate. So remember, these are the main source of hydride ions, which is used for the reduction. So if we have, let's say, aldehydes, so we will get primary alcohol. As you can see in this reaction, it's ethanol, two carbon atom with this functional group. So on reduction, that will give us ethanol, primary alcohol. Is it clear? So basically, as I said, look at that lithium tetrahydroaluminate that is in the form of two ions Li plus 1 and AlH4 minus 1. So overall minus 1 charge. So it means each hydrogen is minus 1 and aluminium is plus 3. So it means overall minus 1 on this complex ion. So same is here. Now on reduction of ketones, what we get, look at that. Hmm. So ketones on reduction, they gives us secondary alcohol. So let's name them. So this one is propanone, right? And on reduction, it is giving us propane 2-ol. You can see it's a secondary alcohol. That is our alpha carbon and two alkyl groups are attached with the alpha carbon with which OH group is attached. And this point is very important. Sometimes in questions they will ask about it. That lithium aluminum hydride is very reactive. So this can be used in the cannot be used in the presence of water. So that can even react with water. So that's why we use dry condition. And the solvent for use for them is this diethyl ether. And the formula of this diethyl ether is this O and then CH2 and CH. So one ethyl group, another ethyl group, in this oxygen, which is acting as a bridge between two alkyl groups, that is ether linkage. So ether with two ethyl groups, so that's why diethyl ether, or you can say ethoxyethane. That is IUPAC name of this compound, which can be used as a solvent as well. Got it? Okay, as I said in on previous page, you can see when we have aldehydes, so on oxidation gives carboxylic acid. So look at this reaction. Oxidation using oxidizing agents, the famous oxidizing agents, potassium dichromate acidified or potassium manganate 7 acidified. So KMnO4, when we heat them under reflux, they will give us carboxylic acid. And this point is also very important that ketones, they do not undergo oxidation. Aldehydes only give us carboxylic acids. You can see here, oxidizing agent ethanol gives us ethanoic acid. And ketones, they do not give oxidation reactions. There is only exception here. So in this case, you can see it's a benzene which is attached with the C double bond O carbonyl group and then methyl group. So phenylethanone, or the common name is acetophenone. Actually, here it is behaving as a ketone group. You can see the carbon on both sides and C double bond O carbonyl group. So that is one exception which on oxidation gives us benzoic acid, which is carboxylic acid. Is it clear? So remember this point regarding your multiple choice questions. Only one ketone that undergoes oxidation, and there is benzene attached with it, which gives us benzoic acid. Otherwise, normally, ketones do not undergo oxidation reaction. Here, reaction with hydrogen cyanide, actually, it's an example of nucleophilic addition reaction. So to remember it easily, you can remember it like this, HCN. So it is an addition reaction. So definitely this molecule will add, CN will add on the partial positive carbon, and hydrogen will add on oxygen. So we'll left with single bond, OH, and a nitrile compound. So hydroxynitriles, that is hydroxy group, and this one is nitrile group. These are the products and the reaction under room conditions. Now, as we know, hydrogen cyanide is a poisonous compound. So what we do for this reaction, we produce this hydrogen cyanide in the flask during the reaction. So for its production, we can use potassium cyanide or sodium cyanide, and we treat them with sulfuric acid. So their reaction with sulfuric acid in situ, that will gives us potassium sulfate and HCN. Here we will get sodium sulfate and HCN. Is it clear? So on addition, nucleophilic addition reaction, that will give us hydroxynitriles. So you can see CN group goes to the carbon and oxygen takes the hydrogen from it. So 2-hydroxy 2-methyl propane nitrile. So here for the naming, carbon 1, carbon 2, carbon 3. So you can see 2 hydroxy propane nitrile. And if you have propanone, so on addition, that will give us 1, 2, and 3. Now there is methyl as well. So 2 methyl, 2 hydroxy propane nitrile. Got it? And the reaction mechanism is nucleophilic addition reaction. So CN goes to carbon and we get this negatively charged oxygen. So this anion takes hydrogen either from the another HCl molecule or from water, which is present as a solvent. And we get this hydroxynitrile product, right? So this is not the part of our syllabus, but let's see here as well. Actually, they are explaining that if you look at the carbon, right? So carbon bonded with oxygen, with hydrogen, and CH3. Remember this double bond or the single bond in the valence shell electron pair repulsion theory. What we learned that single bond or double bond, they behave similar in determining the geometry of the molecule. So here you can see carbon is showing which type of hybridization. Actually, it is showing sp2 hybridization. So it means that is triangular planar structure. Now, nitrile can attack from both sides of this planar structure, either from this side or from this side. So both sides are free. So nitrile can, this cyanide group can attack or from any side. So that can give us two optical isomers. The one is dextrorotatory and the another one is levorotatory, means the one which rotate the plane polarized light clockwise, another one rotate the plane polarized light anti-clockwise. So positive and negative rotation. So you can see they are mirror images and they are optical isomers. Why? Because this carbon is bonded with four different groups. So this carbon here is chiral carbon. So optically active compounds are formed. So that is basically attack of this cyanide group from any side because of the structure of this aldehydes or ketones. The hybridization of carbon is sp2, so triangular planar structure. So this is about the reactions of these aldehydes and ketones. And now next will be our